Air is flowing from left to right through a cylindrical pipe as shown. In this region here and here, the radius of the pipe is r, whereas in this region here, the radius has been constricted to half its initial value. We're asked to find the speed of the air as it enters the pipe. In order to find v1, we will first use continuity to relate the velocity of the air as it enters the tube to the velocity of the air through the constricted region. Then we will use Bernoulli's equation to relate the change in pressure to the velocity of the air as it enters the pipe. And finally, we will use the hydrostatic pressure to rewrite the change in pressure between P1 and P2 in terms of this height differential, delta H. First, we use the continuity equation, which says that the flow rate through any point in the pipe is equal to the flow rate through any other point in the pipe. We choose to look at this point here, where the air enters the tube, and this point here, where the air passes through the constricted region. We write the flow rate as the cross-sectional area times the velocity on both sides, and find that the velocity through the constricted region is 4 times the velocity at this point here. We now apply the Bernoulli equation at these 2 points. We see that the pressure at point 1 plus 1/2 times the density of air times the velocity squared is equal to the pressure here plus 1/2 times the density of air times the velocity here squared. We rearrange the equation to get pressure on one side and velocities on the other, and then substitute in the relationship between V1 and V2 we just found to find this equation here, which describes the change in pressure in terms of the velocity that we want to find. The next step is to rewrite the difference in pressure between P1 and P2 in terms of variables which we know the value of, namely delta H. For a static fluid, the pressure is the same along any horizontal line. So if the pressure is P1 at this surface, the pressure here in the fluid will also be P1 because we can connect these 2 points with a straight horizontal line. We then use the hydrostatic equation to relate P1 is equal to P2, the pressure above the fluid, plus the density of water times gravity times the difference in height between this point and the surface. Moving this pressure to the other side, we now have an equation for P1 minus P2 in terms of terms that we actually know the value of. Putting everything together, we set the 2 equations we derived for P1 minus P2 equal to each other to obtain this result, and then solve for the velocity v1. Plug in the numbers, and find that the velocity of the air as it enters the pipe is equal to 6.6 meters per second.